My name is Shikun Wang, and I'm a PhD student in biostatistics here at MD Anderson Cancer Center. Today, I will tell you a project about the statistical modeling of longitudinal medical cost trajectory with insurance claims data. Healthcare costs in the United States have reached over $20,000 per person for a total of $7 trillion, which accounted for 30% of GDP in the United States in 2020. Due to the escalating healthcare costs and limited resource available, the rising interest in healthcare budget planning increases the importance of statistical analysis of medical cost data. Rapid technology progress in data collection and management allows routinely recorded medical cost data in hospitals and insurance companies, available in nationwide database such as SEER Medicare. So it is desirable to estimate the population average monthly medical cost trajectory from disease diagnosis to death. The National Cancer Institute have published the estimation and projection of cancer care costs in the United States. These papers apply the phase of care approach, which estimate the population mean monthly cancer care cost in 3 care phases: initial, which includes the first 12 months after cancer diagnosis; terminal, which includes the last 12 months before death; and the continuing care, covering the time period in between the above 2 phases. In this bar plot, the light gray areas shows the estimates of the national expenditures for cancer care in 2010, and the dark gray areas shows the projected increase in 2020. Prostate and female breast cancers have highest costs in the continuing phase. The highest increases in the medical cost of care in 2020 were projected for female breast and prostate cancer patients in the continuing phase. This phase of care approach is a simple estimation of the longitudinal cost trajectory as a piecewise constant function with 3 segments, regardless of survival duration. From another figure, monthly breast cancer care costs tend to follow the pattern, which contains data for patients diagnosed during the period of 1980 to 1998. Cost curves were U-shaped, with high costs near the times of diagnosis and death, and lower costs in between. It also suggests that cohorts surviving shorter periods have higher monthly costs in the continuing care phase than longer surviving cohort. Such descriptive plots are intuitive but not smooth and cannot provide more in-depth inference results. In health policy research, log transformation is frequently used to reduce the skewness of the medical cost data. This figure is a descriptive analysis of the monthly medical costs of initial patients and their averages, stratified by the duration of survival since diagnosis. While the individual cost trajectory shows large variations, the average transformed costs appear to be following a U-shape, with higher costs at both tails of the distribution. Such log transformation of the cost data reduces skewness and heteroscedasticity, but not applicable when the data is zero-inflated. Formally, for each patient I, we assume that YIT is a monthly cost, delta TI is the true event time, TI is the observed event time, and delta I is the event indicator. And our goal is to estimate the mean incident cost trajectory as a function of time, conditional on patient's time to death. Several recent papers treated medical costs as longitudinal outcomes and studied the association between covariates and costs using simple parametric functions such as linear or quadratic. Another branch of research used shared random effect models to indirectly handle the effect of survival on cost, but they cannot directly depict the cost trajectory. Our group proposed a semi-parametric joint model to estimating the longitudinal cost trajectory using bivariate penalized splines in an exploitation maximization algorithm, treating the censored survival time as missing data. The algorithm is computationally intensive, and retransformation is needed for inference in original scale. Therefore, developing an approach balances the practical considerations of model flexibility, statistical efficiency, and computational tractability is crucial for the analysis of longitudinal medical cost data. The motivating data set of this paper consists of a national cohort of over 180,000 men who were diagnosed with prostate cancer between 2003 and 2015. The data were extracted from the SEER Medicare database and include medical costs aggregated to monthly intervals from diagnosis to the end of follow-up or death. The overall goal of this study is to quantify and interpret the population mean cost trajectory of prostate cancer patients. The data is right-skewed with 31% zero values. It has several challenges we need to address, including nonlinearity, incomplete follow-up, long-term survivors, heterogeneity, and heteroscedasticity. The left plot shows that the monthly cost data are highly variable and the trajectory of average monthly costs appear to depend on survival. Trajectories generally follow a U-shaped pattern among individuals who die at months 24, 48, 72, and 96 after the initial diagnosis, but an L-shaped curve among those who survive beyond 120 months. The U-shaped medical cost trajectory has been widely reported in the health economic literature, but the L-shape is not well recognized. While the cost trajectory escalates in the months towards the end of life, the increase is continuous without an obvious uptick right around 12 months before death, suggesting a lack of objective justification for the terminal care phase definition. It also supports the notation that the cost trajectory should be estimated as a nonlinear function conditional on survival time, with minimum assumption on the shape of the curve. Both plots demonstrate that the cost data are skewed to the right and have a substantial proportion of patients with zero monthly costs. The idea of our approach is to first estimate header function through a penalized spline regression. Then we specify the mean model of medical cost trajectory to account for both uncensored and censored costs. Variance model addresses the heteroscedasticity of medical cost data. Estimation procedure maximizes a penalized semi-parametric quasi-likelihood. Sandwich estimator allows a joint inference for the survival, mean, and variance of costs. At the initial stage, we only use data from patients who were not censored prior to TAL equals 120 months. The marginal model consists of a two-part bivariate mean model, including the mean model for patients who were dead before TAL and censored at TAL. The covariance model is decomposed by the product of a diagonal matrix and a correlation matrix. This equation 1 is a penalized spline estimating equations with corresponding design matrix and penalty term. The penalty parameter can be chosen through quasi-GCV criteria. Solving the penalized spline estimating equations leads to tilde mu T and S. This estimator is not efficient because it does not account for subjects censored prior to TAL. At second stage, we consider using an available data to estimate the mean and variance of the incident cost of a generic subject I with the following mean function induced by adjustment for censoring. The key idea is to use conditional expectations for GE model to account for a censored covariate, the survival time. And to be consistent, the log hazard estimation of the cumulative density function of survival time is also approximated by penalized splines for the ease of interpretation and variance estimation. Solving the induced penalized spline estimating equations leads to mu hat TNS. The robust estimator for theta tilde is given by this equation 4. In the estimation with equation 2, the survival distribution needs to be estimated at its estimator. While this plug-in approach does not affect the consistency of the point estimator, rigorous variance estimation requires properly accounting for the sampling variability from the estimated survival distribution. For this purpose, we use the following sandwich variance formula for both theta and beta. In our simulation design, time to death tilde t is generated from a Weibull distribution. Censoring time is generated independently from uniform distribution. The true mean trajectory mimics the U and the L-shaped trajectory for long-term survivors. For each subject, the incident cost at time t follows a gamma distribution with a compound symmetry correlation structure. For zero-inflated gamma setting, 50% of responses are randomly set to 0. This figure shows the simulation results in the form of a 2D cost trajectories at selected survival times. To quantify the global performance of our proposed estimator, absolute estimate, and mean squared estimator are further averaged over all the time points as shown in the legends. We find that the proposed estimator fits the mean cost surfaces well under all scenarios. The EM method shows remarkable biases, especially when survival times is large. Global performance in the legend shows that even without using censored cost data, our estimated GE1N outperforms the EM method for both accuracy and efficiency. The proposed GE2Y estimate further reduces the mean average mean squared error by around 50% compared to the EM method for all scenarios, suggesting its superior efficiency and robust finite sample properties. We apply the proposed method to model the medical cost data of a cohort of prostate cancer patients from the SEER Medicare link database and described earlier. The goal was to estimate the population averaged medical cost trajectory stratified by the cancer stage at the time to diagnosis. We specified a quadratic B-spline basis for the medical cost service mu-TNS with 10 equally spaced nodes. This figure illustrates the estimated trajectories corresponding to 2, 4, 6, and 8 years of survival and the long-term survival group over 10 years of survival with 95% confidence intervals. The cost trajectories of all survival groups are U-shaped, except for long-term survivors, which are L-shaped, which agrees with the NCI's face-of-care approach. This is because patients tend to receive active treatments right after the initial care diagnosis or various intensive care near the end of life. However, there are some important data features that are not captured by the face-of-care approach. First, it is not straightforward to define or justify 12 months prior to death as a couple that separates the terminal care phase from continuing care phase. This is most clearly shown among the distant stage patients when the monthly costs increase steadily beyond 12 months. Second, the monthly cost for local regional stage patients elevate steeply around 1 year before death, but the elevation is less obvious among distant stage patients. For patients who die within a relative short time period after diagnosis, the cost trajectories mostly reflected the intensive care treatment in the initial and terminal care phases. The cost trajectory is characterized by a bivariate surface mu-TNS, with S being the survival time and T being the monthly cost. Since the surface is defined on a triangular area, the cost trajectory of the long-term survival group is characterized as a separate curve. The estimated surfaces from the local or regional stage cancer and the distant stage cancer are presented in this figure in both 2D heat maps and 3D surfaces. The surfaces are clearly highly nonlinear and demonstrate complicated interaction between the cost trajectory and survival. The long-term survival group does not have a visible elevated cost at the end because survival time and cost data are both censored at tau. This cost trajectory details cannot be obtained from previous methodology, such as the NCI's face-of-care approach. To summarize all the findings, we propose a novel marginal model and inference procedure for the mean medical cost trajectory in the presence of right-censoring. GE-based methods have been extended to deal with the censored covariate motivated by our data application. Further work will be considered to extend the methodology to modeling median cost or other quantiles. A general methodology to model relationship between multiple baseline covariates and their effects on both varying lengths and the nonlinear shape of the cost trajectories is currently being explored. Thank you for your attention. Please contact me through email if you have any questions.